Hi everyone, I am Dr. T.N. Kavita. In this lecture 6, module 1, we are going to see exponential series. And these are the series e power x expansion, e power minus x expansion, e power x plus e power minus x by 2 expansion. That means the cos hx, sin hx, e power 1, e power minus 1, and e power 1 plus e power minus 1 by 2, and e power 1 minus e power minus 1 by 2 expansions are given here. And e power minus 1, suppose the first term 1 missing means in the right hand side, you have to subtract that one here. E power minus 1 minus 1, e power 1 minus 1 is, and e power 1 minus 2, log 2 minus 1, log 2 minus 1 by 2, then these are the expansions. So the exponential series, what do e and e power x stand for? Prove that e lies between 2 and 3. So e value we know, it is lies between 2 and 3 we know, that we need to prove here. Okay, take limit n tends to infinite 1 plus n the power n, and e power x and means limit n tends to infinite 1 plus 1 by n the power nx. So we know from binomial theorem that if n be less than 1, is it? So from binomial theorem n is less than 1 we know. So 1 plus 1 by n the power n expansion is this one. So now from that expansion we just simplify and remove the n and we can get this series equation 1. Above relation holds good for all values of n. This is correct for all values of n. Choosing n is very larger value means its product 1 minus 1 by n, 1 minus or 2 by n product all tend to 1 only. As 1 by n, 2 by n, 3 by n will tend to 0 because the 1 by n, 2 by n, 3 by n everything are 0, no? So its product tends to 1 only. So hence taking limit of both sides of equation 1, when n is infinite we get. So n becomes infinite. So limit n tends to infinite in this expansion. Okay. So now this expansion we know already we said. Similarly the preceding we prove that e power x is equal to limit n tends to infinite 1 plus 1 by n the power nx, and also limit n tends to infinite 1 plus x by n the power n. E lies between 2 and 3, from this is equation 2, and e lies between 2 and 3. Actually e's expansion is 1 plus 1 by 1 factorial. This is equation 3. Clearly e is greater than 2, that we can conclude from this expansion equation 3. Okay, so now is less than 1 by 2, 1 by 2 square plus etc, and less than 1 by 2 by 1 minus 1 by 2, summing and infinite GP are less than 1. Hence E is less than 1 plus 1 by 1 factorial plus 1, less than 3 from equation 3. Therefore E is greater than 2 but less than 3. E is irrotational. So if possible, suppose E equal to P by Q, where P and Q are positive integers, then E equal to P by Q. Okay. So now multiplying both sides by Q factorial, we get P by Q into Q factorial. So P by Q into Q factorial. So P into Q minus 1 factorial and integer plus this expansion. This is equation 4 and is less than. So finally we get the fraction, that is integer plus fraction I plus f, which clearly observed. Therefore E is an irrational number. E is an irrational number, sorry. E is an irrational number. So it lies between 2 and 3. Okay. Problem for practice. More than 2 we already know. So now it is irrational number, so it like between 2 and 3 only. Okay. Problems for practice now. Find the summation of sum to infinite series. So first we can let it Tn as n cube by n factorial, the general term of the series expansion given. Okay. So write this n cube as n square into n divided by n minus 1 factorial into n. Okay. The n factorial is written like this. One term removed, that's it. From the previous term to, we can write it as a factorial, right? So now it becomes n minus 1, n minus 2 plus 3n minus 2 divided by n minus 1 factorial, and taking the partial fraction, we can find like this. Find the sum to infinite now. So put n equal to 1, 2, 3, 4, and remembering that 1 by minus n factorial equal to 0. Therefore 0, since the 0 factorial is 1. So t1, t2, t3, just you replace 1, 2, 3, 4 means we can find like this and so on. So S infinite is you just add this every series t1, t2, t3, everything, and take the common terms, the first terms separately, that is one series, the second term separately, that is one series, and third terms separately, that is one series. Okay, so this is E and this is E and this is E. So E plus 3E plus E equal to 5E. So show that. Next, 2 by 3 factorial plus 4 by 5 factorial plus 6 by 7 factorial plus etc. equal to e power minus 1. So Tn, general term we can take it. Then the general term is the numerators everything are 2 products. So 2n. The denominators are 2n plus 1. So 2n plus 1 factorial. Now add 1 and subtract 1. Add 1, subtract 1 in the numerator. So now 2n plus 1 minus 1, and now again 2n plus 1 factorial we can write like this. 2n plus 1 you remove and 2n factorial you can write it. So now the 2n plus 1 cancel, 1 by 2n plus 1 factorial it becomes. Now after taking the partial fraction, 1 by 2n factorial minus 1 by 2n plus 1. Okay. Putting n equal to 1, 2, 3, 4, etc. and remembering that 1 by minus n factorial equal to 0. 0 factorial is 1 and so t1 and replacing n equal to 1. Okay, 1 by 2 factorial minus 1 by 3 factorial t2. So adding and taking the common terms separately means it becomes a series e power minus 1. Okay. E power minus 1. All terms you can add now, you can get e power minus 1. This is the summation of the series. Last sum. Show that 3 plus 5 by 1 factorial plus 7 by 2 factorial plus 9 by 3 factorial plus etc. equal to 5e. So now the solution, let the general term and add the 3 plus 3 minus 3 plus 3 minus 3 and taking the partial fraction, put n equal to 1, 2, 3 and find the summation, add all that and that gives e, so 5 into e. Okay, next sum, prove that 1 plus, like that. First you this is the LHS is e plus e power minus 1 by 2 formula, and this one also. So simplify, RHS is e plus e power minus 1 by 2. So 1 plus already is there. So on simplifying we get the solution. Okay. Sum the series. Find the general term and replace n by 1, 2, 3 and taking summation of this we can find the final solution, x plus 1 e power x. Okay. Okay, see you, bye. I will meet in the next lecture. So and then you continue learning of this. Okay, see you, bye. Thank you.